All right, so you want to know more about hydraulic fracturing? Well, get ready to dive in because we're going deep today with some excerpts from a textbook chapter on the subject.
Oh, this will be interesting.
I know, right? Hydraulic fracturing,
Yeah.
fracking as it's often called. It's been in the news a lot. There's a lot of talk about it, a lot of opinions. So today we're on a mission to understand it better. You know, the history, the mechanics of how it actually works, and of course the impact it has.
Right.
And believe me, there are some twists and turns along the way, stuff I bet you didn't know.
Like what?
Like, did you know that this technique, it's been around since the 1940s?
Really? I had no idea it went back that far.
I didn't either. And get this, it's the reason the U.S. has billions of barrels more oil in reserves than we thought we did.
Wow. That's a big deal.
It is. But of course, like with any technology, there are concerns and controversies around.
Sure.
So we're going to make sure we cover all sides of the story, the good, the bad, and well, the complicated.
Sounds like we've got a lot to unpack.
We do. It's amazing how widespread this technique has become. I mean, the textbook says 60% of wells drilled today rely on hydraulic fracturing. That's like most of them.
Yeah, it's pretty much standard practice now.
So what is it about hydraulic fracturing that makes it so essential? I mean, why is it so crucial for getting at those oil and gas reserves?
Well, you've got these valuable resources, right? They're trapped in rock formations deep underground, and just getting to them isn't enough. You need to be able to extract them efficiently, and that's where hydraulic fracturing comes in.
So it's not just about finding the oil and gas, it's about getting it out.
Exactly. Hydraulic fracturing allows us to increase the productivity of wells, tapping into those resources that would otherwise be almost impossible to extract.
It's like unlocking a hidden treasure.
In a way, yeah.
And we're not talking about small amounts here, right? The textbook mentioned an extra 9 billion barrels of oil and 700 trillion cubic feet of gas made accessible through this technology. Those numbers are hard to even imagine.
It's a huge impact, absolutely. And it's been happening for decades, like you said, over 65 years.
Yeah, longer than I thought. You know, it's interesting to think about how it all started. The textbook takes us back to the 1890s, and you're not going to believe this. They were using nitroglycerin to stimulate wells.
Nitroglycerin, like
Oh.
the explosive stuff?
Yeah, the very same. It's crazy to think about it now.
It was a different time for sure. They were desperate to find ways to increase production, and they weren't afraid to experiment, even with something as dangerous as nitroglycerin.
Well, it certainly makes you appreciate how far the technology has come. So how did we go from literally blowing up wells to the more controlled hydraulic fracturing process we use today?
Well, it was a gradual evolution. They started experimenting with acid injection in the 1930s.
Acid?
Yeah. And through that, they made a key discovery, what they call the pressure parting phenomenon. Basically, they found that the acid created these fractures in the rock that stayed open, creating channels for the oil and gas to flow more easily.
Ah, so they were basically making it easier for the oil and gas to escape.
Right. And that led to increased productivity.
A happy accident leading to a major breakthrough.
You could say that. And this pressure parting phenomenon really set the stage for what we now know as hydraulic fracturing.
And that's where a guy named Floyd Ferris comes in. Right?
Yeah. Floyd
The
Ferris.
textbook credits him as the pioneer of hydraulic fracturing, and he worked for Stanland Oil and Gas, I believe.
That's right.
So what was Ferris's big idea? What did he do that was so revolutionary?
Well, he saw what was happening with those acid treatments and thought, what if we could do this on purpose, use hydraulic pressure to create these fractures intentionally?
So he took an existing phenomenon and figured out how to, like, weaponize it for better oil and gas extraction.
Exactly.
Pretty ingenious. So did those early experiments work? Was it an instant success?
Well, not quite. The first hydrofrac treatment, that's what they called it in 1947, it didn't actually change the well's output that much.
Oh, really? So a bit of a setback.
Yeah, but that's how it goes sometimes, especially with groundbreaking technologies. You have to experiment. And sometimes those early failures were just as important as the successes. They teach you what doesn't work, and that can lead you to what does.
Trial and error, pushing the boundaries.
Absolutely. And in this case, their persistence paid off. By 1949, the first commercial treatments were up and running in Oklahoma and Texas.
Okay, so they kept at it. But I read that they had this strange idea back then. They thought the fractures they were creating, they were horizontal.
Yeah, that seems kind of counterintuitive now, doesn't it?
It does. I mean, you're pumping fluid down into the earth, you'd think the fractures would go down too.
You'd think so. But at the time, the thinking was that the weight of the rock above the fracture, the overburden pressure, would force it to spread out horizontally.
I guess that makes sense. in a way.
Yeah.
But the textbook mentions them finding cement in vertical fractures during well cementing. So if they were already seeing evidence that didn't fit their theory, how did they finally figure out that those fractures were actually vertical?
Well, it took some clever research by two guys, Hubbard and Willis, at Shell Oil in the 1950s. And get this, they created a gelatin model to simulate the fracturing process.
A gelatin model. Seriously.
Yep. And their model showed very clearly that the fractures were forming vertically, not horizontally.
Sometimes the simplest solutions are the most brilliant.
Absolutely. But even with that evidence, it still took a while for the industry to fully embrace the vertical fracture concept. It wasn't until the mid-1960s when they developed techniques that could provide undeniable proof that the vertical fracture model was widely accepted.
It's amazing how long it can take for ideas to change, even when there's evidence right in front of them.
Science can be like that sometimes. It takes time for new ideas to take hold.
Okay, so we've got these fractures forming, but what about the fluid itself? I mean, what are they actually pumping down there?
Well, in the beginning, they were actually using crude oil.
Crude oil. Really? But isn't that what they're trying to get out of the ground?
Yeah, no, it sounds counterintuitive. But remember, they were still figuring things out. And using oil-based fluids had some drawbacks. For one thing, it was expensive.
Crude oil is valuable.
Exactly. And it was also messy and difficult to handle. So they started looking for alternatives.
I can imagine. So what did they switch to?
In 1953, they made a big change. They started using water-based fluids.
Water. That seems like a much simpler solution.
And cheaper. Water-based fluids are much more cost-effective and easier to work with. Plus, it opened up a whole new avenue for research and development when it came to creating the perfect fracturing fluid.
I bet. So they switched to water. But I'm guessing it's not just plain water, right? The textbook mentions additives like surfactants and potassium chloride. What are those for?
Well, they each have a specific purpose. Think about what happens when you shake up a bottle of oil and water. You get this cloudy mixture, an emulsion. Surfactants are added to the fracturing fluid to prevent those emulsions from forming.
So it's like adding soap to help things mix together smoothly.
Exactly. It keeps the fluid stable and effective. And then potassium chloride, that's added to protect the clay formations.
Clay formations.
Yeah, clay can be very sensitive to water, and when it absorbs too much, it can swell up and cause problems. So the potassium chloride helps stabilize those clay formations, preventing any damage during the fracturing process.
So it's all about minimizing any negative impact.
Exactly. It's about making the process as efficient and environmentally friendly as possible.
It's fascinating how they fine-tuned this process. They even started using metallic-based cross-linking agents in the 1970s, stuff derived from the explosives industry.
Again, borrowing from other fields to advance the technology. These cross-linking agents were specifically for high-temperature wells, making them much more effective in challenging environments. And the innovation hasn't stopped there. The fluids used today are incredibly sophisticated, designed to minimize any environmental impact while maximizing the effectiveness of the fracturing process.
It sounds like a whole science in itself.
It is. It's constantly evolving.
Well, let's talk about another key ingredient in this process, proppants.
Proppants.
Yeah. These are the materials they use to keep those fractures open.
Right. Yeah, so you create this fracture, but it wants to close right back up. So you need something to prop it open, keep those channels open, so the oil and gas can flow freely.
So it's like putting a doorstop to keep the door from slamming shut.
Exactly. And in the early days, the proppant of choice was, you ready for this? Sand.
Sand, like from the beach.
Well, screened river sand, to be precise. It sounds simple, but it turns out sand is really effective.
Back to basics. But I'm guessing they didn't stop there. They must have tried all sorts of things, right?
Oh, absolutely. They experimented with everything.
Okay.
Plastic pellets, steel shot, glass beads. They even tried nutshells.
Nutshells, really. That's amazing.
It's true. But after all that experimentation, they found that sand was actually hard to beat, especially a specific type called -20 to +40 mesh sand.
So sometimes the simplest solution is the best. But have the ways they use sand changed at all over the years?
Absolutely. The concentration of sand they use has increased dramatically. They used to use less than 1 pound of sand per gallon of fluid, and now they're using anywhere from 5 to 8 pounds per gallon, and sometimes even 20.
Wow, that's a lot of sand. So we've gone from basic pumps and river sand to these highly engineered fluids and prop pans. I bet the equipment needed to handle all this has also undergone a major transformation.
Oh, definitely. The evolution of equipment is a whole other story. In the early days, they were just repurposing cement and acid pumps, and some of those early pumps were even powered by surplus WWII aircraft engines.
Aircraft engines. Seriously.
Yep. But as operations got bigger, they needed more power and precision, so they switched to powerful diesel engines. And now there's talk of a potential return to turbine engines for even greater efficiency.
Wow, it's come full circle. I remember reading about those contrasts in the textbook, like going from 75 horsepower pumps to over 15,000 horsepower,
Sure.
and from pumping 2 to 3 barrels a minute to over 100 barrels per minute in shale gas plays.
Yeah, the advancements have been pretty amazing, and it's not just the pumps either. They've developed these specialized blenders to mix and pressurize the fracturing fluid, making sure it's got the right consistency and pressure. There's one called a slinger pump that uses centrifugal force to mix the proppant with liquefied gases.
Okay, that one I got to look up.
Okay.
But with all those millions of pounds of proppant being used, how do they even manage the logistics of it all?
It's quite an operation. They used to just use dump trailers to transport the proppant, but now they've got these sophisticated systems with conveyors and gravity silos to make sure the proppant flows smoothly from storage to the well site.
Like a well-oiled,
Uh,
or should I say sand-filled,
mm,
machine.
aha, exactly.
And what about the equipment that actually transports the fluid down into the well? Those pipes and connections must be incredibly strong to handle all that pressure.
You're absolutely right. They use these specialized swivel joints called chicksons that allow the pipes to move in 3 dimensions so they don't break under the intense pressure. They're pretty critical for making sure the fluid gets to where it needs to go safely and efficiently.
Wow, it's amazing how every little detail has been thought out and refined over the years. But I imagine that designing and planning these treatments must have been a real headache back in the day. How did they figure out the right parameters for each well?
Well, in the beginning, they were using all sorts of charts and nomographs and doing a lot of manual calculations.
Sounds complicated.
It was. But then in the 1960s, things started to change with the advent of computer-based modeling. There were these pioneers like Perkins and Kern, Christianovich and Zeltov and Geertsma and de Klerk who developed the foundation for simulating hydraulic fracturing processes on computers.
I think I've heard those names before. What did they do that was so revolutionary?
They were the first to come up with mathematical models that could predict how the fractures would form and how the fluid would flow. This was a huge breakthrough. It meant engineers could now simulate the whole process on a computer, experiment with different parameters, and optimize the treatment design for each specific well.
So it's like they created a virtual lab where they could test things out before actually doing it in the real world.
Exactly. And today, those models are incredibly sophisticated. We're talking 3D finite element models that can simulate the entire fracturing process in amazing detail, predicting everything from the shape of the fractures and the way the fluid moves to temperature profiles and even how much production they'll get.
It's mind-blowing to think how far they've come with this technology.
Yeah.
And speaking of advancements, we've been talking about vertical wells, but what about horizontal drilling? How does hydraulic fracturing fit into that picture?
That's a great question. Horizontal wells have become really popular, especially for those unconventional shale formations. And hydraulic fracturing is a key part of that technology. But there are some unique aspects to consider when you're fracking a horizontal well.
Okay, so horizontal drilling is a whole other ballgame. I'm intrigued.
We'll get into all the details in just a minute. So horizontal wells, right? They've become super popular lately, especially for tapping into those unconventional shale formations. And hydraulic fracturing, it's a key enabler for this whole horizontal drilling thing.
Yeah, I can see why horizontal drilling would be advantageous. I mean, you're basically extending the reach of the well bore, covering more ground, getting to more of that reservoir. But you mentioned some unique considerations for hydraulic fracturing in these horizontal wells. What makes them different from the vertical wells we were talking about before?
Well, one key difference is what we call near wellbore effects. It sounds kind of technical, but it's basically referring to the area right around the wellbore where they inject the fracturing fluid and where the fractures start to form. And in horizontal wells, managing this near wellbore region, it becomes really important because you've got this much longer wellbore and the fracture networks can be a lot more complex.
That makes sense. More area for things to potentially go wrong.
Yeah.
The textbook also talked about this special technique called frack and pack, something they use in poorly consolidated rock. What's the idea behind that?
Oh, frac and pack. It's a pretty clever combo of hydraulic fracturing with some sand control measures. You see, poorly consolidated rock, it's basically like loose sand. And when you try to fracture it, the sand can easily move into the wellbore and clog things up, which causes all sorts of
So
problems.
it's like trying to build a sandcastle with dry sand. It just falls apart.
Exactly. So, frack and pack. It tackles this problem by combining the fracture stimulation with some hardware that prevents the sand from migrating into the wellbore. It's a two-in-one solution, you could say.
It's amazing how they've come up with these specialized techniques for all these different geological challenges. But getting back to horizontal drilling, what's the main reason for this shift? Why go horizontal instead of vertical?
It's all about maximizing contact with the reservoir. Think about it. You've got this layer of rock with oil or gas in it. With a vertical well, you're just punching a hole straight down, so you only access a small portion of that layer. But with a horizontal well, you can extend the wellbore horizontally through the layer, which means you're exposing a much larger surface area to the oil or gas.
Ah, so it's like casting a wider net to catch more fish.
Exactly. More contact equals more potential for getting those resources out. And when you combine that increased contact with hydraulic fracturing, which makes the rock even more permeable, you get a really powerful combo for unlocking the potential of these reservoirs. And this is especially true for those unconventional plays, like shale formations, where the oil and gas are really tightly trapped.
It's incredible how technology has opened up access to resources that we couldn't even touch before. But of course, with any powerful technology, there are concerns, right? I mean, we can't ignore the elephant in the room, the controversies surrounding hydraulic fracturing.
Yeah, it's a complex issue for sure, and there are definitely some valid concerns that need to be addressed. But I think it's important to approach this with a good understanding of the science and to be able to separate fact from fiction.
The textbook makes a clear distinction between issues caused by wellbore integrity and those related to the fracturing process itself. What's the difference there?
Okay, so think of the wellbore as this pathway, this pipe, that connects the surface to the reservoir deep underground. If that wellbore isn't built right or sealed properly, you could have leaks or contamination.
So in those cases, it's not the actual fracturing that's causing the problem, but a failure in the wellbore itself.
Right. Wellbore integrity is super important, and any issues related to leaks or contamination, they usually stem from problems with well construction or cementing, not the hydraulic fracturing process itself.
That's a really important distinction. But even if the wellbore is perfectly constructed, there are still potential concerns about the fracturing process, right? Like, what about the amount of water they use or the potential for triggering earthquakes?
You're right, those are valid concerns, and the industry is working on addressing them. The American Petroleum Institute, for instance, they've developed new standards for hydraulic fracturing operations that focus on environmental safety and wellbore integrity. These standards, they really emphasize doing things responsibly, like minimizing water use, managing those waste fluids, and monitoring for any seismic activity.
So they're being proactive. But what about people who say that fracking is inherently dangerous and should be banned? What do you say to them?
Well, any industrial activity, it's going to have some level of risk, and there will be impacts. The key is to weigh those risks against the benefits and to put strategies in place to minimize any negative consequences. Banning a technology completely without looking at the whole picture, that can have unintended consequences too.
It's about finding that balance, meeting our energy needs, but also protecting the environment.
Exactly. And technology is helping us find that balance. The industry is constantly innovating, coming up with new ways to reduce the environmental footprint of hydraulic fracturing. They're making progress in areas like reducing water usage, recycling fluids, and even developing proppants that are more environmentally friendly.
That's good to hear. So we've talked about the history, the mechanics, the controversies. It's a lot to digest. What do you think are the main takeaways from our deep dive so far?
Well, I think one of the biggest takeaways is that it's not a simple issue. It's not black and white. There are valid concerns, but there are also significant benefits, and people are working hard to address those concerns.
It's about having those conversations, listening to different perspectives, and making informed decisions.
Absolutely. We need to look at the science, the economics, the social benefits, and the environmental risks. It's through open dialogue and finding common ground that we can figure out how to navigate these complex challenges and create a sustainable energy future.
Well said. This deep dive have given me and hopefully our listeners a lot to think about. We've covered a lot of ground, but I feel like we've only scratched the surface of this fascinating and often controversial technology. What are your thoughts on that?
I agree. We've touched on the history, the mechanics, the challenges, the opportunities, but there's always more to learn. The technology is always evolving, and our understanding of what it all means, it's constantly deepening.
And that leads us to a question for our listeners. What are your thoughts on this whole balance between getting the resources we need and protecting the environment? How do we make sure we have the energy we need without damaging our planet?
That's the big question, isn't it? There's no easy answer. It's different for every situation. You have to think about the specific context, what technologies are available, and the values of the people who are affected.
It's about finding solutions that work for everyone, both now and in the future. We have to think about what we need today, but also make sure we're not messing things up for future generations.
Right. It's about finding that sweet spot, meeting our needs without sacrificing the needs of those who come after us. And that's a responsibility we all share.
Absolutely. Well, this deep dive has been eye-opening for me, and I hope it sparked some curiosity for our listeners, too.
Yeah.
What are some things that stood out to you during our exploration of hydraulic fracturing? What questions are you still thinking about?
I'm curious to know what parts resonated with our listeners. Did the history of the technology surprise them? Were they aware of how much they use computer modeling to design these treatments? Or maybe they're wrestling with the ethical questions about energy needs versus environmental impacts?
It's definitely a topic that's ripe for discussion. As we wrap up this deep dive, I want to leave our listeners with one final question to ponder. What innovations in hydraulic fracturing could further minimize the environmental impact while making it even more efficient?
That's the question that's driving a lot of the research and development in this field. It's a challenge that calls for creativity, collaboration, and a real dedication to progress.
We've already seen some amazing advancements, and I'm sure we'll see even more groundbreaking innovations in the future.
I'm optimistic about it too, and who knows, maybe one of our listeners will be inspired to contribute to those innovations. Maybe they'll be the one to come up with the next big breakthrough that makes hydraulic fracturing truly sustainable and environmentally friendly.
That would be incredible. Imagine being able to get the energy we need without harming our planet.
It's a goal worth striving for sure.
Definitely. Well, I think it's time to wrap up our deep dive into hydraulic fracturing. It's been a real pleasure exploring this complex and fascinating topic with you, and I hope our listeners enjoyed it as much as I have.
It's been great to share my insights and get into this topic with you and our listeners.
And to our listeners, thank you for joining us on this journey. We hope you've learned something new and that you've gained a better understanding of hydraulic fracturing, how it's evolved, the impact it has, and the ongoing efforts to address the challenges that come with it.
And remember, this is just the beginning of your exploration. If you're curious, keep digging, keep researching, and keep those conversations going about the future of energy.
And if there's another topic you'd like us to deep dive into, just let us know. We're always looking for new adventures in knowledge.
Until next time, keep those minds curious and those questions coming.
Happy exploring. You know, it really feels like we're at this turning point with hydraulic fracturing. I mean, we've seen so much progress, but there's still so much room for improvement.
Oh, yeah. It's a really exciting time to be working in this field. Everyone's pushing for cleaner, more sustainable energy, and that's driving some amazing advancements in hydraulic fracturing technology.
It's like we're just scratching the surface of what's possible. It makes you wonder, what's next for hydraulic fracturing?
Well, one area I'm really excited about is water management and waste reduction. Imagine if we could create a closed-loop system where all the water used for fracking is completely recycled.
That would be huge. No more worries about using up freshwater resources.
Exactly. And what if we could develop proppants that are not only effective, but also, like, biodegradable or even beneficial to the environment?
Wow, proppants that actually help the environment, that would be incredible.
There's some really smart people working on it. Imagine proppants that break down into harmless substances over time, or even, like, enrich the soil. It sounds futuristic, but I think it's within reach.
It's amazing to think about. You know, one thing that really struck me during this deep dive is the sheer ingenuity behind hydraulic fracturing. I mean, from those early days with nitroglycerin to today's sophisticated computer models and all these specialized techniques, it's been quite a journey.
It really shows you what humans can do when we put our minds to it, solving complex problems. And I think that same drive to innovate, it's going to keep pushing hydraulic fracturing forward.
I agree. And who knows, maybe one of our listeners will be inspired by this conversation, by this deep dive, and contribute to those future innovations. Maybe they'll be the one to develop that breakthrough technology that makes hydraulic fracturing truly sustainable and eco-friendly.
Wouldn't that be something? The future of energy is literally in our hands. It's exciting to think about what we can achieve together.
Absolutely. Well, I think it's time to wrap up our deep dive into the world of hydraulic fracturing. It's been a fascinating journey. I hope our listeners enjoyed it and learned a lot.
It's been my pleasure talking about this with you and sharing these insights with our listeners.
And to our listeners, thank you so much for joining us. We hope you've gained a better understanding of hydraulic fracturing, its history, how it works, the impact it has, and all the efforts being made to make it safer and more sustainable.
And remember, this is just the beginning of your journey. Keep learning, keep researching, and keep those conversations going about the future of energy.
And if you have any other topics you'd like us to deep dive into, let us know. We're always up for exploring new and interesting subjects.
Until next time, keep those minds curious and never stop asking questions.
Happy exploring.